Hey, what's up everyone? Jason Turley here, back with another video, and I've been doing a side quest the last couple months of learning about smart contract security and blockchain security and learning solidity and things like that. So I wanted to showcase a resource, a capture the flag called Ethernaut from the amazing company Open Zeppelin, and they've put together a series of challenges. Let me actually go back to the home page here. We can scroll down and we can look and see that there's currently 33 different challenges. And here at the bottom, the note talking about it, let me move myself out of the way. It says the Ethernaut is a Web3/Solidity-based war game inspired by overthewire.org, which we do have videos on this channel showcasing. Those are the more traditional cybersecurity, reverse engineering, binary exploitation, and web kind of CTFs and war games, whereas Ethernaut is focused on Web3 and blockchain in this new programming language called Solidity that we will dive into throughout this series. Each level is a smart contract that needs to be hacked. The game is 100% open source, and all levels and contributions are made by other players. And then it's saying if you have any interesting ideas, you can feel free to showcase and submit those here. We'll be focusing on level 1 today, called Fallback. So this is the makeup and the structure of the game. We scroll down and we see we have a bit of a description. It tells us to look carefully at the contract code below, and you can win the challenge. You can beat the level if you are able to do these two things. If you can claim ownership of the contract, so we'll get into what does ownership even mean and how can we become an owner of a contract, and then if we can reduce the contract balance to 0. So if we can somehow drain all the funds, all the money, all the virtual make-believe monopoly test money that's in this contract, if we're able to reduce all of that to 0. And then it's telling us we can look into these things if we need additional help or tips and whatnot. And then down below this, we have the actual source code of the level, just perusing at it. If you are familiar with Solidity or JavaScript, this syntax is very similar, but we're not actually going to solve this challenge here in the web browser. If you want to, go ahead and do that. If you're comfortable doing it that way, you have to deploy a testnet and MetaMask, which is a wallet that you can use. And it is a little bit like tricky if you've never done stuff like this, and getting funds from a testnet is hard because you have to fork over real money, and we don't want to do that. So instead, we're going to go to this repo, Ethernaut X Foundry, and I'll leave a link to this in the description down below. This has all of the challenges for the Ethernaut CTF contained in a Git repository that we can clone, and we can run it in our local setup. So we'll be doing that in Visual Studio Code, and we'll walk through the different levels, and we don't have to fork over any real cash. We don't have to worry about setting up MetaMask or a wallet or any of these extensions. So to get started, you can simply click on this big code button down below and git clone the repo, and you will need a few tools as well. You'll need Foundry, which is a testing framework, and this is very, very simple to install. If we click here on the installation page, we can see we can install it with one command by curling this website and piping that directly into Bash. Hey, quick disclaimer and warning, doing this isn't recommended most of the time. Be sure you trust the website that you are grabbing the code from, because what if this was like a incorrect URL or phishing and you're just running whatever random script you got from the internet. But I have done this. This is safe. You can run this curl command and pipe it directly into Bash, and then you run the command Foundry up, and this will install the latest stable version and all the different binaries that you will need for the actual testing framework. So to get started, we're going to open this up in Visual Studio Code. You see here, I already have the repo installed in my system, and I'm opening it up in Visual Studio Code, and we can look at the different layout. But for us, all we are really concerned with is the contents of this SRC directory, the source directory. We can see here, it has all the names of the different levels. We have Fallback and .sol, which is the Solidity file. This is the .sol is the extension for Solidity code. So we'll be working in this file, and all of the levels will have a factory associated with it. This is just something behind the scenes for actually running the challenge level. You can look at it if you want, if you're very curious, but we will only need to work with fallback.sol for this level. We don't need to worry about any of the factories. and behind the scenes setup and initialization. But if you are curious, feel free to poke around and look in the different folders. There's a lib folder for different libraries and modules. There's images, there's the output, so the compile with output and things like this. But for us, we're really just going to be focused on two folders, right? The source folder, and if we scroll down within there, we see a test folder. So the test is where you're actually going to be running your code, running your exploit, your proof of concept to beat the level. The naming convention for this will be the name of the level, so fallback, and then .t for test, and .sol or .sol. So we can open that up as well. And if we do a quick peek of this file, we can see a bunch of garbage. It looks like a bunch of nonsense, right? But if we just look at some of the function names, okay, setup. So we're setting up some type of environment, setting up different addresses, different players, and we can see here these comment sections. So any level setup and initialization goes here. The level attack, this is where we will be writing our proof of concept in this section, and then the behind the scenes, how the challenge will actually be submitted and validated, right? But let's actually look at the contract code. We have not done that yet. We've done a lot of talking, but we haven't actually looked at any source code yet. So you'll notice what I have here inside my Visual Studio Code will be a little bit different than what you see here on the main Ethereum page. And that's simply because the version of Solidity, which is the programming language, changes very rapidly. So if we see here, at the very top line, it says Pragma Solidity 0.8.0. So this is just the different versions of the programming language, or rather the different versions of the compiler, because the language gets updated very often. And then if we go to our Foundry, we see it ends in .10, which there's a comment here saying this is the latest Solidity version. But if we actually come over here to DuckDuckGo and just type in Solidity version, we see that actually 0.8.29 is the latest version. So what does that mean? This programming language and just things in Web3, blockchain, smart contract, crypto space, things change rapidly, right? A few years ago, the main testing framework were things like Hardhat and Truffle, and now they're moving over to Foundry, which is what we'll be using throughout this series. So things change very, very quickly. So that's why some of the things you see on the main Ethernaut website, even though it's a great CTF, it is a tiny bit outdated. So in this Foundry repo, they did have to modernize some of the code or change a few things. And where they do make changes, they'll add comments as well. But for the sake of simplicity, let's just look at the code provided on the website right now. So that way, if you're solving it on the website or the Remix IDE or Foundry, at least we all kind of have the same starting point. So just looking through the code, we see here, we have a contract called Fallback. If you're familiar with object-oriented programming, you'll know things like classes. A contract is essentially a class. It's a way to group different things together into one, instance, one object. We have a mapping. So a mapping is very similar to a dictionary or a hash map. It'll take an address and it will map to a number, an unsigned integer. So contributions. So someone can send a contribution and it will get stored here in this dictionary or this mapping. And we have an owner that is of type address. Addresses are essentially ways to keep track of different users, different accounts, different wallets in Solidity and Web3. These are different than addresses in the sense of like traditional computer science, when we do like reverse engineering and an address is like a pointer. This is very different. So try not to conflate those two terms. An address, when it comes to Solidity and smart contracts, essentially means a user or some type of wallet, someone sending a transaction. Next up, we have a constructor. The constructor runs exactly one time when this contract is first deployed onto the blockchain. That's when the constructor is run, and anything inside of it will take place. So usually things will get initialized here. We can see that the owner is being set to the message.sender. All this means is the owner is the person who deploys the contract. This is called access control. So perhaps you want to allow privileged functions that only the owner, the person who deployed that smart contract, can do. Maybe you don't want any user to come in and make changes to the protocol or to the project, you only want the owner or someone that you allow, like an admin, to make different changes and pauses and these privileged operations, right? So the owner is being set to the person who deploys the contract. And we can see that the owner will initially deposit 1,000 Ether, 1,000 Ethereum to the contract. Okay. Here we have some more special Solidity stuff, something called the modifier. So this is kind of like a access control, a shorthand, almost like a function. So a modifier called only owner, and all it's saying is the person who is calling a function, the person who's trying to do something, they must be the owner of the contract. So we'll see later on when this only owner modifier actually gets applied. But essentially, it's just a way to lock down the contract, do some access control, that only this special person can do these things. Next up, we have a contribute function. Public payable. Public, all that means is it can be called by anyone. There's no access control. It can be called from inside this contract or from without the contract. And then payable, it can send and receive money, essentially. So we can send money to this function, we can contribute. However, we must contribute less than this amount, 0.001 Ether. We can't send any more than that. So we can only send a fraction of money, a fraction of Ethereum, essentially. So assuming we send enough money, we will pass this check. The require keyword is essentially like an assert statement in other languages. This has to be true, or else the rest of the code will not execute. It'll just error out, essentially. So if we do send enough money and we pass this check, down here, we will be added to this mapping of this dictionary, and our value will be stored. So if we send like 1 Ethereum, we will be added to the array with a value of 1 Ethereum. And every time we add more, it's essentially just keeping track of how much money we've contributed or donated in this protocol. And now this if statement. So if the person who just submitted a transaction, if their total contribution is more than what the owner of the protocol has contributed, update the new owner. So message.sender isn't like a static value. Every time it's from the context of whoever sends a transaction. So if like Bobby sends a transaction and he calls this function, he is the current message.sender. If Alice calls the function, she's the message.sender. So it's a weird, special, reserved variable in Solidity. MSG, message.sender, it's whoever is currently sending or starting that transaction, right? So the contribute function, to summarize it, you deposit money, and if you deposit more money than the current owner, then you are the new owner. It's kind of like King of the Hill. You gave the most donations, so you have this privilege of ownership. But we see here that the owner deposited 1,000 Ethereum. So it's going to be very difficult to deposit more than that, right? Especially because we can only deposit a fraction of that at a time. So this will be very difficult to get this test case to pass. But let's keep looking through the code and see what else we can do. There's a function called get contribution. It's a view function. Essentially, this is just a getter. So it's just going to return how much money that we currently contributed. Nothing more, nothing less. It doesn't make any changes. All it does is essentially print out and return how much that you have submitted, how much you have donated to this project. And then the next function is called withdraw. And we see this only owner. That should look familiar. If we scroll up a few, we see this modifier called only owner, and it's saying require that the person who's sending this transaction is the owner. If not, error out with this print statement, with this like alert. So the caller is not the owner. And this underscore, I guess what's the best way to explain this? So whenever you see this only owner modifier, so right now there's a require statement here, but when we have the only owner modifier, essentially what it's doing is copying this highlighted line and it's putting it right here in the beginning. So maybe this is where I'll open up the editor, because we can kind of play around with this a little bit. So the only owner modifier. What exactly is it? So anytime this tag, this modifier is added to a function, it'll essentially grab this line and paste it. So we have only owner here. This is essentially just saying paste in this require statement, and then the underscore semicolon essentially just means run the rest of the code. So essentially this is what this is doing, right? If I take out this, this will work the same way. So if I call the withdraw function, first it's going to do this check. It's going to say, hey, are you the owner of this contract? Are you the owner of this protocol? If not, error out. Only the owner can transfer money. So this line right here, it's almost best to read it backwards. So owner.transfer address of this.balance is pretty confusing. But if we read it backwards, it's essentially saying, so this is a special keyword. It means the current contract, so the Fallout contract. So the balance that is within the contract, all the money that all the people have contributed. So take that balance and transfer it to the owner. So you have to kind of read it backwards for it to kind of make sense. And that's because the Solidity programming language is just weird. Crypto, Web3, blockchain, it's just kind of weird. So that's essentially what this function is doing. And then last but not least, we have this fallback function. So a fallback function, a receive function, these are things that get executed when you send money not to a person, but directly to the smart contract itself. So the smart contract, the thing that's deployed on the Ethereum blockchain, the code that's running, you can send Ethereum to it, or money, way, whatever you want to call it. You can send money to it, and it will trigger this fallback function. Okay, so the last function we'll look at is the fallback function. And if we do look at the code here, we see it's called receive. So there's two ways you can send money to a smart contract, right? That piece of code running on the blockchain. It will either have a receive function or a fallback function. For all intensive purposes of this challenge, they're essentially the same thing. If you don't provide either a receive or a fallback function, a default one will be given to the contract by default. Essentially, all it is a way to handle the contract receiving money. So if you are sending money, Ethereum, whatever, to the contract, however much money we send, it must be greater than 0. And it will look us up in the contributions dictionary, and the balance must also be greater than 0. So we must send more than $0, and we must have already contributed to this before. And if we do, we see this. Owner equals message.sender. It's being typecasted here. That doesn't really matter. Essentially, it's updating the new owner. So if we can send money to the, so if we can send money with the contribute function, will be added to that contributors array or dictionary. And then if we send some more money directly to the protocol, we will become the new owner. And as the new owner, we can call the withdraw function and transfer all of that sweet funds directly to us. Okay, so this is the test script, the Foundry test suite, essentially, where we will be writing our exploit proof of concept or proof of code. And we can ignore a lot of the setup for this video. Essentially, we're creating an EOA address, an externally owned account, and we're giving it 5 Ethereum just to fund them initially. So we will be able to solve the level. And then we can see here, we're actually creating the level instance and we're deploying it. And our fallback function is given the name Ethernaut fallback. So we can actually do things like Ethernaut fallback and then hit period. And we can look at things like the current owner, or we can call different functions like contribute and whatnot. So this is how we'll actually interact with the different functions inside this smart contract. So before we actually start writing our proof of concept, it might be good to annotate what we want to do with some comments. So coming back, we know we want to become the owner. That is our goal. We want to become the new owner. And if we just try to call withdraw, it'll fail because we're not the owner. This is a privileged function. It's locked down with access control. So we know we can become the owner by sending money directly to the contract, because that will trigger this fallback function. However, we will fail these 2 checks. We will fail this check because we are not currently added to the contributions or the contributors array, right? So in order to get added to that array, to that mapping, that dictionary, we need to call the contribute function. So the syntax for this will be a little weird, but we want to say contribute, contribute to the cause, right? And then we want to send money directly to the protocol. And then finally, call withdraw. And then we can do like some checks and verification and whatnot. So contribute to the function. So we want to call Ethernaut fallback.contribute. We can see I have an extension installed where I can kind of just highlight and look without having to switch back and forth between the folders or the files. So contribute, it takes no arguments, but how do we get this? How do we get that message.value? How do we actually send money? So this is where the syntax gets a little wonky. It gets a little ugly. So let me zoom in to make sure we can all see. So if I call this function as it is, this will not do what we want. So let's actually test this. So forge test tac-tac-mt to specify I only want to run a single test case. I want to run forge test fallback hack. And we see that the level does fail. If I scroll up a little bit and I add tac vvv, we should be able to see why it failed. Okay, it's not showing exactly why it failed, but it failed because we didn't actually send any money to this. We sent a balance of 0. So it does pass this check, right? Because message.value is 0. So we are added to this array, but this case won't work. So let's actually send some money. So this syntax does look a little bit ugly. You need to add these curly braces. And then inside the curly braces, you're essentially making a dictionary or a mapping. So we want to say value is one way. We see here that 1 Ethereum is 1 way with 18 zeros after it. So a way is like the smallest possible value when we're talking about Ethereum and cryptocurrency like that. So we're sending a tiny bit of money. And now we need to send money directly to the contract. And once again, forgive me, the syntax will be a little bit ugly, but we want to typecast this contract to an address. And then we want to do .call. Again, we'll have parentheses. This is where you can send any call data is what it's called. So if we want to specify a certain function, we don't want to for this. So we're going to just put 2 quotes, just an empty quote. And then just like before with these curly braces, we want to add that to our call function as well. So we're going to paste that in there. We're sending just a tiny bit of money just to pass these checks. We see it is highlighted in this yellow squiggly. If I do hover over this, it's saying return value is not used. It's not really necessary for this level, but it will return a tuple. It will return a Boolean saying whether or not the call was a success. And it will return some call data as well, but we are leaving that empty. And then it's going to just be upset because we're not actually using, and we're fine with the yellow squiggly, the compiler warning. Now we want to actually call the withdraw function. So just do Ethernaut fallback.withdraw, because now we should be the owner. If we want, we can do an assert equal that the contract's owner is our EOA address. So inside the fallback function, we see this public global variable called owner. Since it's public, it automatically has a getter method. So it allows us to look at the value. So that's why we need to add these parentheses, because hey, even though this is a variable, we're kind of calling a method on it, the view method or the get method. Then we do our withdrawal. So at this point, the balance of the contract should be 0. And I think that's what's getting checked in this level submit down here. But we can be explicit and we can check that ourselves here. So let's do another assert equal. We want the Ethernaut fallback contract dot balance to equal 0. And if we're not sure what this is to begin with, we can just grab this here and let's go to the very top. Let's say emit log named uint. We'll say fallback, contract balance. And then for the value, we'll paste in the actual balance of the contract. Save it with Control S. And then let's run this. If I just do a forge test, it'll run every single test case that we have here in all of our test files. So I just want to narrow it down to one. So what is this called? Let's scroll down here. Test fallback hack. So let's run that. And I need to add a tech VV so I can actually see the logged output. So we do get a lot of compiler warnings, but if I scroll up, where's it at? Where is it at? Oh, here. Fallback contract balance is 0. So everything passed. Why is it 0 at the beginning? That's weird. It should have some type of funds. So that's weird that the contract balance is 0. Let me just try this to play around with. vm.deal address of Ethernaut fallback. Let's do 100 Ether. Save this. Rerun it. Okay, so whatever was going on in the setup, maybe something was overlooked. It seemed like the starting balance was 0. So let's actually do this again. Let's copy here, and I'm gonna change this to starting balance, and down here, even though we have this assert, let's just do it again, and we'll call this ending contract balance just to make it explicit and clear. So we hit up arrow and run this. So let's rerun this test. Okay, cool. So we can see the starting contract balance is 100 Ethereum, and then it ends with 0 Ether. We successfully drained it all. And I guess just for laughs and giggles, we can look at our contract. So player funds or player balance, whatever you want to call it. If you want this to be the EOA address, we can see what we currently have. So we have our 5 Ether that we started with, as well as the 100 Ether that we drained from the contract. So hopefully that was fun. Hopefully that made a little bit of sense. The video is a little longer than I intended it to be, a little bit of yapping, a little bit of rambling, but I did kind of want to go slow. This is my first time ever showcasing any Ethereum or blockchain or Solidity on the channel. I'll keep making some of these videos if you guys find them interesting, and I will kind of crank them out a little more quickly as we continue to grow and learn and get comfortable with this programming language. And if you are comfortable or you do want to follow along, by all means do. And if anything is confusing, remember, it's not your fault. It's not a lack of knowledge or anything. This is just a weird programming language. Blockchain, crypto, like all this stuff is weird. It's not very intuitive, and like, what is this Ether stuff and why is this payable? And so as we explore more of these challenges, you will see that the Solidity programming language is just kind of weird and it updates all the time. So if you're using older resources to learn it from like 3 or 4 years ago, it's kind of outdated from the current stuff. But with all that out of the way, hopefully you guys like this video. Please like, comment, subscribe. Let me know if you want to see more of this stuff in the future. And as always, guys, take it easy, and I will see you in the next video.